The first material I want to share is this. You remember that when we have transpose of a product, this is equal to, you flip the order, okay? And then when you have transpose of summation, what happened with it? This will be, which is also equal to, summation, you can switch the order. Okay. However, with this multiplication, you cannot switch the order. Cannot switch unless they are the same. Okay. Is this okay, Sean? Okay. However, if it is the inverse of the matrix, okay, then this will follow the format of the transpose, which is B inverse times A inverse. Okay. Now, however, when you have the summation and then you take the inverse, they are not the same with the inverse, then you sum it. They are not the same. Okay. I think in some meetings I said that they are not the same. The multiplication, the product, they are the same. Yeah. The one that's not equal is when you have summation, you take inverse, it's not the same with this. Okay. Okay, let's move on to the next material. This you will see this later when we compute the inverse of a matrix. So our topic today will be vector spaces up to the dimension. The material is a lot of material in here. So I think it will take up one meeting. Yeah. I will start with a question. Let's say we have linear equation ax equal to b. Yeah, A is a matrix, x is a vector, and b is a vector. So from this equation, which one is the solution? X is the solution. Yeah. So from this equation, we want to find what is x. Okay. And then we want to find non-trivial x. What do we mean by non-trivial? Non-zero x. Okay. If x is all zero, it is not counted as a solution. Okay. It is called trivial solution. Skip it. The matrix A, it can be viewed element wise. So I write down here elements of A, n by n matrix. In this case, I take an example of square matrix, but it can also be rectangular matrix. And this is the x from x1 to xn, and this is b1 up to bn. If I want to see it column wise of A, I can say this, a1, a2 up to an, like that. So from a1 to an1, I call it a1, vector a1. For a vector, I make a notation of bold notation, or sometimes you can also do make an arrow on top of the letter. That's a vector. My first question, can anyone answer this? What makes solution X unique?
It only has one answer.
Huh?
It only has one answer.
Sorry?
It only has one answer.
What's the condition for that? We studied last week. Last week. Anyone remember?
That it's non-zero.
Huh?
That it's non-zero.
There is non-zero. What happened with the zero? X non-trivial. Okay, not that one. Sorry? Huh? At the A. I don't understand what's at the A. Okay, you remember that last week when we do Gaussian elimination, we try to make matrix A to be what? Upper triangular, yeah. You see, the bottom part is all 0, okay, and the upper part is non-zero. Some of them can 0, but we want this to be generally non-zero. If this is upper triangular like this and there is no 0 row, then the solution is unique. Yeah, you get what I mean? For example, if we have 1, 2, 3 here, 4, 5, 6, and this is, let's say, 7, 8, 9. What is x3?
3. 1.5.
The last equation says what? 6x3 equal to 9. So what is x3? It's 9 over 6. Not correct? It's correct? Or your logic is not catching up yet?
That's right.
Huh? What about your common sense? Hey, no response at all. Come on. Hey. No, I see your face spacing out. What about x2? So you have 4x2 plus 5x3 equal to 8, yeah. You plug in x3 9 over 6 here, you get x2. Okay, and then the same thing for x1. So in this situation, your solution will be unique. Yeah. So what does it mean here? The requirement for solution X to be unique is that you can make that A, row reduce it, okay, using Gaussian elimination so that it becomes upper triangular matrix with non-zero rows. If you can do that, then the solution X is unique. Okay? Understand this? Yeah. And one of the material that we'll discuss today is the rank of the matrix. Not today, maybe in this week. Yeah. And this situation is the same as saying that A is full rank. Okay. So this situation is equivalent. This is equivalent, yeah. A inverse exists. Yeah, A non-singular. What else? Determinant of A is non-zero. What else? A full rank. They are the same condition. Okay. So if A satisfies any of these conditions, then we can make A to be this. Okay. Then the solution is unique. Full rank is when your columns are linear independent or rows are linear independent. Okay, which we will see later. Okay. So that's the condition for X to be unique.
Determinant A inverse 1.
Determinant, we will study it later. Yeah. A inverse also we will see later. Yeah, which is why I want to open up the problem now so that we know what we are studying. The next one. So we know that the condition for X to be unique is that matrix A to be full rank, yeah, or A inverse exists, determinant of A is non-zero. So with that, if that happens, my second question, can we choose any B here to guarantee that X exists? Can we choose any B? Anyone know what does it mean by any B? Any number of B, correct? Yeah. It is real number, yeah. Let's say I have a problem 1203. Okay, B1, B2. This is upper triangular matrix with non-zero rows. Okay, so it satisfies that condition. Solution X unique. So can I plug in any B in here? Let's say B1 in R and B2 also in R. Can I choose any B1, B2 real number? Can? Yes. The answer yes, yeah. So B matrix B, vector B, this is in R2, yeah, correct? That's in R2. What do we mean by choosing any B is that we can choose any point in the XY plane to become B. Yeah, any point in the XY plane. Okay, and the answer is correct. We can choose any B to guarantee x-axis. What's the reason? The reason is that B exists in the range space of A. Okay, so this situation, yeah. If we want to choose any B so that it applies here, yeah, the condition is that B, it has to be in the range space of A. That's the condition. Okay, because A is full rank, the columns of it are linear independent. Okay, the columns of A span the entire XY plane. Okay, because A inverse exists, and then determinant A is non-zero, and all of those conditions, yeah. The effect is that columns of A spans entire vector space. So this is what we will see. So you need to understand what is vector space, what does it mean by span. Yeah, span means linear combination of vector. Yeah, so if I wrote down based on the columns of A, yeah, I have A1, A2 up to AN. Let's say this is X1 up to XN equal to B. Yeah. How do we write B? B is equal to this multiplied by X1. Yeah, so the B is A1 times X1 plus A2 X2. Okay, so if these columns of A spans the entire vector space, then we can choose any B from that vector space. This is called span. Okay, my next question, if let's say columns of A are linearly dependent. Linearly dependent means determinant of A is 0, A is singular, A inverse do not exist. Can we choose any B to guarantee X exists? So it's the different situation. Yeah, in here linearly independent, this one linearly dependent. For number 1 and 2, solution X is unique. For number 3, solution is either not zero, non-existent, or infinitely many solution. Non-singular means determinant is non-zero. Same. Yeah. What about number 3?
Yeah.
If number 2 we can't choose any B, then number 3 of course we cannot. Okay. So only we can only take a part of it, apart from the vector space, to take B. Yeah. So let's say if we have a situation where you row reduce the column of A, and one of the row is 0. Okay, let's say one of the row is 0. So it becomes 0 in here. Yeah. So what we can see here is that 0 times x2 equal to b2, yeah. And then we have x1 plus 2x2 is equal to b1. And then 0 times x2 is equal to b2. So the condition for this is that what happened with b2? What is the condition for b2 so that we can find x1 and x2?
0.
Yeah, b2 can only be 0. Yeah, you get it? You don't get it? What if b2 is 1? Can we find x2?
Every number
Unmodifiable.
divided by 0.
Huh? Yeah, if b2 is 0, then x2 can be any number. That's what it means. So in this situation, b2 can only be 0. Yeah, b2 can only be 0. If b2 is non-zero, we cannot find the solution. Can you see this? Who cannot see? Can you see it? This is so small. Can you see from there? Yeah. So the only admissible b2 is just b2 is 0. Okay. If b2 is 0, what happened with x1? So x1 plus 0 equal to b1. x1 equal to b1. Okay. So b2 is equal to 0 and x1 equal to b1. So that means we can choose b1 to be any number, but then b2 has to be 0. Yeah. So in xy plane, where is that? In xy plane, if we have b1 and then 0, b1 can be any number, but the second element can only be 0. Where is that in the xy plane? Middle here.
It's 0.
Can I choose b1 to be 1?
Yes.
Can? So it's here, yeah. This is 1, 0. Can I choose b1 to be 5? So it's here, yeah. 5, 0. Can I choose b1 to be minus 3?
Yes.
So it's here, yeah. Minus 3, 0. So where is this?
The horizontal line.
That's the horizontal line, yeah. So it's this one. Okay. So this defines a line, yeah. A line in a plane. A line in the xy plane. Okay. XY plane, because we are working in R2, this XY plane is our vector space. And because B can only be taken from this line, yeah, so we say that B exists in the subspace of our vector space. Okay, you know what does it mean by subspace? Sub means below, right?
A space within space.
A space within space, but the quality is below. You are my sub, like saying, yeah. If I say you are my sub, then the one that I say is lower than me. Okay, subspace is lower than the vector space. Lower in what sense? Anyone know? The size, the dimension. Okay, the vector space xy plane, how many dimension? Two dimension. Yeah, dimension in this line and then dimension in that line. Yeah.
For now, it's
Now I'm saying the vector space
the
xy. The whole thing
okay.
is two dimension. Yeah.
Okay.
Now this line only one dimension. So the subspace has lower dimension. Yeah. But then we will learn later. For a space to be a vector space, to be a subspace, it has to satisfy certain conditions. Okay, a certain condition must be satisfied. So clearly, when your A is your A is singular, A inverse do not exist, determinant A is 0, A is not full rank, then not any B can be applied there. Yeah, not all B is admissible. For sure, guaranteed. Yeah, which is why you will find out a problem which has no solution. That is, if you take B from other space. Yeah, so admissible B is from here. If you take B, like for example here, you cannot find solution. Yeah. Yeah, let's move on. So for this situation, where does admissible B lies? This is admissible. What does it mean by admissible? Admitted. Yeah. So for the above case, linearly independent A, B, you can take it from the whole vector space. Yeah. However, when A is not linearly independent or linearly dependent, then B can only be taken from its subspace. Yeah. And that's the topic for today. We are done. Yes, that's only that much. Now, any question before I start doing the topic in order? But we will take only a bit, because these are the whole topic for today.
Can the subspace be y-axis?
We can. Yeah, it really depends on the A matrix. Yeah. Any question? For which case? X2. X2 here is non-zero. Yeah. Okay. 0 x2 equal to 0. Because B2 can only be 0, yeah. So the equation is like this. 0 times x2 equal to 0. Okay. So what is x2 here then? Any number can, right? Yeah. So x2 is free to choose in this case. Okay. Yeah, another example is this one. If I have 2 minus 2 and then minus 1 1 like this, and then this is x1 x2. What if we row reduce the whole thing? What is it? If we want to row reduce the A, what do we do? Okay, we write this, yeah.
I'm half or 1.
So row 2 minus plus row 1, yeah, plus row 1. So it becomes 2 minus 2, this is b1 is 0 0, and then 2b2 minus b1. Okay, so what does the situation right now for b? Admissible b in this case, we know that 2b2 minus b1 must be 0, yeah?
or wait,
Yeah, so b2 must be b1 over 2.
Okay.
Yeah, so now the situation for b is that we have b1 free to choose, but b2 can only be b1 over 2.
yeah.
Okay, where does this lie?
B1 is the
Uh, it's this, yeah. It's this line where the slope is half. Yeah, if b1 is 0, then b2 is 0 also, right? If b1 is 1, what is b2?
half.
Half. So you have here 1 comma half. What if b1 equal to 4?
2.
Yeah, 4 comma 2, right? So you get this line, and that is a subspace also in the.
Oh, it's a subspace.
That is also a subspace.
It's a diagonal.
This is also diagonal. If you see, like from this side, it becomes diagonal. A subspace always pass through the origin. A vector space is passing through the origin.
Condition.
That's the condition. If it doesn't pass the origin, it's not a subspace. Okay. Any other question? So we have a lot of terms, yeah. Vector space, range space, span.
So is the origin always 0 0?
Yeah.
So,
Yeah.
subspace bisa kayak satu kuadran gitu, Mas.
Subspace no, cannot.
Ini masih
Yes. Yeah, there are some rules on the subspace which we will discuss later. The first thing is about field and vector space. But the most important thing you have to remember is that when we are working with R2, yeah, our vector space is the whole xy plane. Okay, and then what is the field? Our field is the real number.
Oh.
Okay, so the field is like the association of the elements lah. Our elements is the member of real number. Okay, so our field is real number.
And when it is R3, it's still number.
Yes, when you are working R3, R4, R100, the field is still the real number, but then the vector space changes the dimension. Yeah. If it is R3, it becomes X, Y, Z, so it's become a three-dimensional space. Okay, the vector space. Yeah. So when we talk R2, our vector space is the whole XY plane, the whole out of this boundary of the class, all of them in. Yeah. Okay, so I don't want to discuss all of these axioms. You read this on your own. Okay, this is important, very basic thing, will not be asked, but this constitute the field. Okay, for example, we can create a new field if the new field satisfy all of this. Yeah, if you want to work in mathematics, you need to know how to make a new field, so it has to satisfy all of this. And then for the vector space, it's just like we discussed. Yeah, these two must apply for a vector space, and this one you need to know. Addition and scalar multiplication is closed. Yeah, so you see, if I have 1 over half in there, I multiply with -5. Yeah, what I become?
Minus
1 1 and 1. Sorry. Too many things to write. If I have a vector 1 and half, if I multiply this by -5, then it becomes -5 and then, okay. So because this is a subspace, the resulting vector will also be in that subspace. It's over here, yeah. It is not going out from that subspace. Okay. So does it mean by scalar multiplication is closed? If you multiply a vector in a subspace by a scalar, then the resulting vector will still be inside that. Okay, another example is that we have one half and then 4, 2, yeah. What if we add them? Plus 4 and then 2. What does it become? 5 and then 2.5. Are these inside the subspace also? Yes, yeah, because this is half of that. Okay. Getting to understand now? The R2 vector space. Okay. When you add a vector in here with a vector in here, what's the result? It is still a vector inside the xy plane, right? It will not be a vector that is outside of xy plane. It's still there. Yeah? You get what I mean? Okay, yeah? Oop. Yeah. These are all axioms for the vector space. So if you want to check whether a vector space is a vector space, you have to check all of this. These are an example of common vector spaces. Continuous function. This is y equal to mx. So the one that we discussed just now, it's a vector space. The subspace is just like what you said, is a space inside a vector space, okay, with a dimension lower than that. So this is the definition. Okay. And then an example will be here. Okay, let's test. So you just apply this rule to check whether it is a subspace or not. For number 26, do you think this is a subspace or not? So how do you read this? How do you read this? The W is a space consists of x, y, and z. And the condition for that is that x plus y plus z must be 0. Any x, y, z satisfying this, then it is a member of the W. So yeah, how do you write this is as a vector? X plus y plus z equal to 0. How do you write it as a vector? X plus y plus z equal to 0. What is y?
Minus x.
Yeah, minus x minus z. What is z? Okay, so if you write down the vector, this is x and this is minus x minus z. And then okay, minus x minus but the y itself is this, right? So back to the Z again. Okay. Let's just do this lah. And then now you apply this, yeah. You can take Z from any number. Okay. Let's say I will have X to be 1, Z to be 1. What is my vector in here? 1, and then this is -2, and this is 1. Okay. Another thing is that if I take X to be 2, Z to be 2, 2 minus 4 and 2. If I add these two, what does it become?
Yang atas -2.
3 minus 6. It's true, right? Okay. So when we take a member of that W, add them up, it's still W also. How do we know it is still W? It satisfies this equation. Okay. Understand? Who don't? Need to repeat this? Alfred? Yeah, which one? Which part that you don't get it? Louder.
The X plus Y plus 0 is
Yeah.
the vector is variable.
Yeah, the same variable.
Only have the variable.
Yeah, X and Z.
Now, how you make the one?
Oh, okay. So based on this, I can choose any X. I can choose any Z. Okay, and then the Y must satisfy this because of that condition. But I can also choose, let's say, X equal to 1, Z equal to 2. What does it become? -1, -3, and then 2. Okay, and then let us add this with 3 minus 6 and 3. What does it become? This is 3 minus 9, and this is 4, yeah. Sorry, 4. It's 4. So we add them up, it's still 0, yeah. Yeah. In fact, you can choose any number, X and Z, any number can. Yeah. Number 26 is true, number 27 is false. Yeah. So you know how to check, yeah. Number 27 false, and I will let you to check. For those who haven't checked, you can check on your own. Yeah, it's easy. Okay, can we move on to the next topic? Okay. Subspace we discussed already. Another example of subspace you can read on the module, yeah, on the module, which I will not discuss in the class. And now it's about linear independence. Yeah, the thing that we discussed in the beginning. Okay, guys, we are having a notation in here, v1 up to vm. Okay, v is the vector, and c1 c2 up to cm is a variable. It's a real number. Okay, and this format that we have here is called linear combination. Yeah. How do we know if a vector is linearly independent or linearly dependent? Is that we see through this equation only. Yeah, you only check that equation. So if let's say you have a matrix 1, 2, 3, 4 like this, yeah. How do you create that? You create the C1 times 1, 3 plus C2, 2, 4 equal to 0. Okay. So what do we do with C1 and C2? Any idea? Okay. If the only solution to this equation is C1 0 and C2 0, then it means these columns are linear independent. If the only solution is C1 0, C2 0, then this is linear independence. Okay. And in fact, this is linear independent. You cannot find C1, C2 unless it is 0 to make this true.
Oh, we check the C1 and for real numbers.
Yeah. You check. Huh? You do it faster. You just need to know whether or then can you express that factor by a multiplication of another factor? Can you do that or not? If you cannot, then it is linear independent. It's easy.
Jadi kalau 1, 2, 3, 6 itu linearly dependent.
1, 2, 3, 6, yeah, linear dependent. Correct. Because that column is twice of the first column. Okay. Yeah. And then another thing to check is that you do row reduce. Row reduce using Gaussian elimination. If you find one of the rows are all 0, then it is not linear independent. Now, one of the row. Okay. If you want to row reduce this, it will just become like this, because this is linear independent. It will become upper triangular with non-zero rows. However, if you have 1, 2, 3, 6, just like Sean said, yeah, you row reduce it, it will become 0 in here. Okay. How come this one is linearly dependent? If you apply this, what is C1 and C2 in here? Huh? A1 0 plus C2 A2 0 equal to 0. What is C1 and C2? Huh? You cannot choose both to be 0. No, cannot. So we know that we have C1 A1 is equal to minus C2 A2, yeah, like that. And so, yeah, C1 in here is just minus C2 A2 over A1. And you can choose C2 to be any number. You don't get it.
I don't get this one.
I'm asking you, this column is twice of this column, right? Okay. Now, because it is twice of that, we know it is linearly dependent. Okay. Because linearly dependent, we can transform it into a row reduce factor, a row reduce matrix, where one of the row is all 0. Okay. So we know already that this is linearly dependent. Then we want to check using this concept Yes, C1 dependent on the C2.
Oh,
Okay, so we can find non-zero C1, C2 so that this equation holds. Okay. Yeah, another. I think I have another example like later. The second way is here. You read it on your own, yeah. Okay. The same definition. Now you check the linear independence of this, Johan. 1, 2, 3, 4. Just we have here. This is linearly independent. What about 1, 4, 4, 16? Dependent, yeah, because the second column 4 times. 4 times of the first column. Okay. What about this one? This is twice, yeah. Michelle, is it okay? What about this? Number 28. Yeah. If it is linearly independent. Yeah, correct. No relation. Yeah, yeah.
So the first one you write yeah. When
Collection of column factors in R2 are independent. Correct? True or false? You said what? False?
independent.
Or what?
Why is this independent? False.
I don't understand. Repeat again. Say that again.
Oh wait,
Saying
it's false.
that
It's false.
it's
It's false.
Dependent because
it's dependent.
You say they are dependent?
Yeah.
Yeah, we'll see.
kan kalau di row B is Gaussian, satu per satu berapa?
Okay, we have 1, -1, and then -1 and 1. Okay, you say that this vector is -1 of that, yeah? Okay, so they are dependent. Okay, so the answer is false, yeah? Because this is dependent.
Can we use like the Gaussian from you plus it to the bottom 1 minus 1?
You get 0.
Yeah,
Yeah, you can also do that. If you can do that, then it is dependent.
jadi kita gabungin ini combine the two.
But all of them has to be 0, yeah? Not just one of the element.
But this was in all.
If you add them, then it become all 0, then you can do that. Okay. What about this? Are these 3 columns linearly independent or linearly dependent? Yeah.
Independent.
Computing the determinant is the fastest way, yeah. Determinant of this is 0.
Independent.
Yeah.
Kalau 0 independent.
Huh?
Independent.
Yeah, we add them.
Independent.
We add this, it becomes 0. It's dependent. Okay.
Oh, okay.
And then if I ask you how many of these columns or how many rows are independent or dependent, what to do? How many of them? Yeah, how many that are independent? How many are dependent? What's the rank? This rank is 2. You check. The rank of this is 2.
What is rank again?
Later we will learn about the rank.
Oh,
Yeah.
belum tahu kan. I haven't noticed.
Haven't unlocked it yet.
What's the rank? The rank is 2. It has to be 2.
Dari mana?
Okay. So how do we know that the rank is 2? Now you convert this into the upper triangular matrix. Okay. We will eliminate -3 and -2 at the same time. What to do? Yeah. What to do?
So row 1 times 2.
Row 1 times 2?
Yeah.
No.
Times
One times
1
1.5.
times 3 minus.
Or make it simpler. Let us make it simpler lah.
Apa tuh row 3 minus 3 row 1?
Kalau Gaussian row.
Just like this.
Yeah.
Okay. So we plus this, yeah.
Plus.
Row 3 plus row 1, and it becomes this is 0, and this is -3.
3.
Just 3, yeah. Okay. Now what to do with this? Row 3
Plus 3 row.
plus 3 row 2. Okay. Then it becomes
Minus 1.
okay. It's all 0.
Yeah.
So can you see how many rows that are independent? We only have 2, yeah.
Oh, right.
For the last part, it is dependent.
Only XY.
Yeah, it's only XY.
If we find a value on the last row, are they the full rank?
Yeah. So you see, this first column and the second column, they are linearly independent. Okay, linearly independent. These two, but this one and this one is not. Yeah. Let me say to you, yeah. 2 0 0 and then -1 1 0. These two are linearly independent. Okay, we cannot find any number C1 C2 to get this to be 0. We cannot. Yeah, however, the last one is dependent to the second one. Okay, you add them, it becomes 0. Okay, so these two are actually the same vector.
They're equal to 0.
You add the third column and the first. Sorry.
No, it's not 0. It's always -2.
Oh, this is -1, yeah. Oh, if we add these 3 together, sorry. Add these 3 together, it becomes 0. Sorry, yeah. Not this, the second and the third one. We add the first, the second, and the third one, becomes 0. Okay. So we can only find 2 independent factors. Yeah, based on that, the rank is 2.
We add them, get 0, it's independent.
So you're saying
No,
that,
it's dependent. We add this, you get 0.
Yeah,
It's dependent.
it's dependent.
Yes.
So you're saying the third row is dependent on the whole thing.
Yeah.
Bukan cuma yang minus one.
Yeah. So I can say that 2 0 0 plus -1 1 0 is equal to the third column. Okay, which is 1 and 1. So that means the last column can be expressed as a linear combination of the second and the first column. So the last column is dependent. Okay.
Dependent.
Yeah, I jump a bit to count how many linearly independent columns and rows in this case, yeah, so that you can get the rank of it. 29. Are these independent?
That's
101 and then
Yes, independent.
011.
Yes,
independent.
independent.
Yes, you can clearly see it is independent, yeah. So the answer is true for 29.
The whole column is independent.
Yeah, they are independent on each other for this case. Okay, I will skip on this. You study on your own. I think you can do this already. Yeah. Now about the span. Just now I discussed about the span. So this is the definition of span. Do you mind if you read it for a while? Read this while I'm erasing this. Brian, are you catching up? Span. Okay, so based on your understanding, what is span? I asked you to read, right? Yeah?
Oh, finite.
Correct. It is all finite linear combination. Okay. So span will tell you whether the linear combination will fill up what kind of vector space. Okay.
Limit negative.
Yeah.
Span is the limit negative.
No. Yeah, for example, our favorite example, yeah, this one. This column, if I say C1 13 plus C2 24, this one will span the entire R2. So let's say this is B1 and B2, yeah. Because these two columns are linearly independent, okay, the linear combination of this can fill up the entire XY plane. Yeah, so the span of these columns are R2. Yeah, not 2. The span is R2. That's the way we say it, okay? Because the columns of this matrix is linear independent, so the linear combination of these columns spans the entire XY plane. When I say span, I will do this. Span the entire XY plane. Okay. And then another example that we have 1 minus 1 minus 1 1. This one only spans what? Yeah, it spans a line. Yeah, it spans only a line.
How do we write it?
No. Not span is what, but it will span something. Okay. The columns of this, it will span R2, or it spans the entire XY plane. But the columns of this spans a subspace in R2. Okay. That is the definition of the span. Yeah. So I want to repeat again. If we want to make a condition so that any B admissible to the problem, yeah, then the columns of A must span the entire vector space. Yeah. Is this okay? Or not okay? If you have a
What's the
span and rank,
yeah.
rank is integer. Yeah, you say a number. Is it 1 or 2 or 3? Rank is the number of linearly independent columns or rows in a matrix. Okay, and span, you say it like this: the columns of A spans R2, spans R3, spans R4, or spans a subspace in R3. Okay, so we are not saying a number when we say a span. Yeah, it also say here spans of that is a subspace of a vector phi. Alfred, is it okay? Okay, how about the span? Michelle? Okay, Johan. Okay, let's move on. Okay, what's the span of this?
R2.
R2. And the span of this will be a subspace in R2. Yeah. Yes, this one also,
Subspace in R2.
the span is a subspace in R2.
But we're gonna have to specify the same subspace.
Yeah. Yeah, you see how they ask about the span. The collection of vectors span R3.
True.
Okay. True, because these are linearly independent.
Yeah.
Okay, so it will span R3. What about this? Span of this is equal to span of that. If that's the question, then what is I, K, and J here? You know? Yeah, I minus K, comma J is written as, sorry, let me write it. I minus K, comma J.
Why not?
How do you write this? This is 1, 0, 0 minus, what is K here?
0 minus.
0, 0, 1, yeah.
Oh, yeah.
And then comma, what is J? Okay, so therefore you will have what? This is 1, 0, minus 1, and then 0, 1, 1. Okay, this is the I minus K, comma J. What about I, J, K?
1, 0.
Okay, versus,
Yeah.
okay, and the answer is false, yeah? Okay, false, because this one will fill up the entire R3, and this one is only a subspace in R3. Okay, now you get it. This area, do you get it? Okay, read it. Clear? Okay. Yeah? How do we what?
Do we get the one?
This?
Yeah, that,
The first column is just I minus K, right? This is I minus K. So 1, 0, and then minus 1, right?
yeah.
And then the J is just Oh, the J, yeah. Sorry. J is just. I see why you confused. This is 0. Sorry. It's supposed to be 0. Yeah. Although this is linearly independent, but we have only 2 factors. Yeah. It's not enough to span the whole R3.
Oh, jadi R2 itu R3.
Yeah. Spans R2. This is spans R3. Okay. Let's move on. Yeah, before we discuss the basis, I will take a break of 5 minutes. Okay, let's begin. Okay, a basis is a collection of vectors. Okay, so basis is a collection of vectors, but those vectors must satisfy these 2 conditions. The first one is that they are linearly independent, and then these vectors span the vector space. Okay, and if that happens, then those vectors forms the basis for the vector space V. Okay, for example, if we have 1, 0, 0, and then 0, 1, 0, are these linearly independent?
No.
This linearly independent or not?
No. Dependent.
It is linearly independent.
But row is 0.
No.
One of the rows is 0.
This column, I mean.
The column is
No.
No, it is not. The last row is not linear independent, correct? What about the column?
Linear.
The column is linearly independent. Okay. You don't understand? The column. This is column. This is row. Yeah. So the column are linearly independent. Okay. However, are this column spans R3? Huh? Are this span R3 or not? Now you understand span. Just now you don't understand span, right? You can answer. Yeah. So it's correct that these 2 columns do not span R3. So that means these 2 vectors cannot form the basis for R3. Okay, what about this then? Are these columns linearly independent? Yes. Are these vectors span R3?
yes.
Yes. So these columns
Basis R3.
form the basis for R3. Okay. What is the meaning of basis then? In that case, any idea?
Minimum condition to.
Yeah, the meaning of a basis is that, because just as you said just now, basis is the basic. Okay, so it is a basic factor from which you can create all factors in that space. Okay, if you take linear combination from a basis, then you can fill up the entire vector space. That is what it means by basis. Yeah, is this okay? Yeah, if we are using this, can we create a vector of 5, 6, and 7? Can we create 5, 6, and 7 from here? Yeah, 5, 6, and 7. How many? This. Yeah, only 2 factors, right? Can I create 5, 6, and 7 from these two vectors? Cannot, right? Because the last 0, yeah, we cannot find 7. However, if I create using these vectors, I can do that. Okay, 5, 6, 7 is equal to yeah. What is C1, C2, and C3 in this case? 5, 6, and 7. So clearly 1, 0, 0, 0, 1, 0, 0, 0, 1 is a basis for R3 because using linear combination of these vectors, I can create any vectors that I want in the R3. Okay, that is the definition of basis. Not always. That this is the condition. Yeah, if this condition is satisfied, then that's basis. This is just an example, very easy example. Identity matrix. Okay, a notation now. The notation that we have, if it is E1, then this is a 1, the rest are 0, E2, 0, 1, and something. So the subscript correspond to the non-zero element in that vector. So if I have to define what is EI, what is EI? EI is a zero row or columns or column, yeah, where the ith element is equal to 1. Okay. Yeah, Alfred. Okay. Zero row of columns, so everything is 0 except the ith element be 1. Say that again. Oh. That is the problem. Okay, this one. Number 32.
Yeah.
Can this form a basis?
Yes.
So you have 1 minus 1 and then 0, 1, yeah? Yeah, 1, 0, and minus 1 and 1. So this is true, yeah? Any question on this? This is true? The first thing is that they are linearly independent and then they span R2. Okay. They span R2. What about number 33?
The collection of vectors from a basis of
Yeah, you see, we have only 3 elements in a vector, right? But then you have 4 columns. Only 3 vectors maximum that can be linearly independent. The fourth one must be dependent. So this one is false in this case, yeah. So this is false. Let me give you an example. 1, 0, 0, 0, 0, 1. If I give a number here 3 minus 2 and then 7, I have 4 columns, yeah. These 3 columns linearly independent, okay? What about the fourth one? Are these dependent to the tree? This one, are these dependent to the tree?
No.
Yeah.
Dependent. No.
Not dependent? No. Okay. Now if I write down can I find C1, C2, C3 so that this one holds?
Yeah.
Yeah, so the last one dependent, okay? The last one dependent. So if it is these three only, then it forms the basis, but with the fourth one, it's not the basis.
33 is 4.
False.
Also.
It is false. Not. Because, yeah, the fourth one is not independent. It's not dependent. It spans R3, yeah. It will span R3. It spans. But one of them is not linearly independent. So it is a opposite case from this example, yeah. This example, linearly independent but not span. Okay? But this one, span R3 but not linearly independent.
Span R3 but not linearly independent.
Tapi artinya true kan?
So
Which one? This?
No.
It's not the basis.
Basis.
Problem 33. So it's true.
No, it's false.
It still forms the basis of R3.
It's not the basis for R3.
The basis for R3 needs to be independent.
You have to satisfy two conditions. The first one, linearly independent, and then it spans.
Good dependent.
Okay. Number 33, it spans R3, but the fourth one is not linearly independent. Okay.
It's 3 times 3.
Not 3 times symmetric. R3 means 3 by 1 factor.
By
R3 means 3 by 1 factor. This is a member of R3.
3 by 1.
3 by 1 factor. But when we say vector space R3, then it is a 3-dimensional space. Okay. Two different things. Is this okay? Alfred, do you get it now? Okay. Yeah. So the example over here, only 2 columns. They are linearly independent columns, but it doesn't span R3. So it is not the basis for R3. But for this one, the columns spans R3, but one of them is not linearly independent. So it is not the basis. Same thing. Before I go to the row and column rank, let us finish this. What do you think the answer is? So we have a subspace. J is the Z, yeah.
J is the citizen.
Why will number Z to 0?
XY is free, but Z has to be 0. Z has to be 0. Yeah. So K. Huh? Do we have 0 in K? No. Let us understand the problem first. Yeah, you don't understand the problem. The problem here asks you to find the basis for a subspace. Okay, and the subspace is defined by x, y, and this is 0. So you can choose any number in x and y, but z has to be 0. Okay, what is an example of this? An example of a subspace satisfying this? Example is 1, 1, 0. What else?
0.
2, 2, 0. What else? Yeah, 3, 5, 0. The last element is 0. Now you just see the list of answer in here. What is I, k? I, k is what? Anyone know? 1, 0, 0, and then 0,
1.
0, 0, 1, yeah? So, is this satisfying this?
No.
Huh? No, yeah, because it has a number in the z.
Berarti A dong.
Okay, so any any answer has k is not the answer. Okay,
Oh, so it's A.
let us check whether this is the answer or not. Okay, the first one is I, j, I minus j, yeah, and then I plus j. So this is 1 minus 1. Sorry, 1 minus 1 is 0, yeah. 1 minus 1 is 0, and then the next one 1, 1, 0. Okay, so are these linearly independent?
Linearly independent.
These two columns, are they linearly independent or not?
Yes.
Yes. Column, yes, because this column cannot be expressed as this column multiplied by any scalar. Cannot. Okay, and then are these two columns span xy? Yeah, the question, is it span R2? Answer is yes. Yeah, because they are linear independent, and then when you take linear combination, it will only fill up the space in R2. So the answer is A in this case. So the basis is not just for vector space, but also for subspace. Yeah, it can be discussed for that. Okay, now about rank of a matrices. This is the definition: maximum number of linearly independent row vectors. Okay, that's called row rank. So you only need to find out how many linearly independent vectors, independent row. Yeah. If it is column, wait, where is the column? Okay, if it is column, the row rank of a matrix A equals the maximum number of linearly independent column vectors A. Okay. So in fact, the row rank cannot exceed the column rank. Yeah. They will have the same rank for the row and the column. Okay. So this matrix, what's the rank of this matrix? The rank of this matrix? 2. Yeah. What's the rank of this then? 3. Yeah, correct. You just count how many linearly independent. If you can see it by your eyes, just right. Okay. But if you cannot see, for example, you cannot see clearly, let's say, yeah. Like this. Can you clearly see if this is linearly independent or not? If you cannot see, you reduce the row so that it becomes upper triangular matrix. Okay. How do we make it upper triangular matrix? Row number 2 minus 4 row number 1 ya. Row number 3 minus 7 row number 1. Then it becomes what?
1, 2, 3.
Huh? The rank is 3, yeah, just want to show. This is 1, 2, 3, and then
0
0. What about this?
minus
5 minus 8 minus 3, 6 minus 12 minus 6. This is 0. 8 minus 7 times 2, 8 minus 14 minus 6. And then minus 6 minus 21 is minus 28. Okay. Now we reduce again this one. What do we do? R3
minus
plus plus 3 times R1 ya. R3 plus 3 R1.
Bukannya masih pakai R2.
Sorry, R2 ya. We have to use R2, correct. So minus 2 ya. Minus 2 R2.
Minus 2 R2.
So we have 1, 2, 3.
0
This is 0 minus 3 minus 6. This becomes 0.
0
Minus 28 plus 12.
16.
16 minus 16. Okay. Now you see this. We can clearly see that this one and that one and that one are linearly independent. Okay. There is no 0 rows, 0 columns. Okay. So rank is 3. So my advice is that if you cannot see at a glance, you take the Gaussian elimination.
Do the row plus row.
You can do that.
Can do that.
You can also do that. Yeah. If they are linearly dependent, it is easy ya, Dylan.
Yeah.
You can do that, Dylan. If the matrix is linearly dependent, you can do that. But if it is full rank, it is not easy to see whether it is you cannot find C1, C2, or C3. It's not easy to see that. Okay. So the same method is explained here. You only need to compute how many row that has no 0. Yeah. If it is this case, then what is the rank of this matrix? 3, yeah. If we can reduce it up to this format, then it is only 3. 1, 2, 3. The last row is not independent. Okay. Okay, the basis. Now this matrix, yeah, this matrix, after I reduce it up to this, then this columns forms the basis for matrix A. Okay, so once you do this form, then this is actually the basis for the column space of A. Okay, rule 1 number 2, you see. The rank of this from 3 to 9 times 3 ya. Number 1.
Wait.
This is 1. Rank cannot be 0 lah.
Oh, yeah, 1.
1.
What?
they are dependent on each other, like the whole row and column.
One. The answer is one. Yeah. So column number 2 is 1/2. Yeah. It is 1/2.
Rank ya?
Yeah, the rank. You try to get the rank of this. What about number B? Rank A is 1. What about B? What's the rank of B?
Sir, why is the rank A is 1?
It is 1.
And
Only one factor that is independent. The other two is dependent on this. You see what I mean? This one is independent. These two dependent on this one. I can express column 2 using column 1. I can express column 3 using column 1. So column 1 is the prime column. Okay, which is why the rank is 1. We can. You choose column 3 to be the prime, so we can express column 2 and column 1 as a multiplication of column 3. So only one independent factor. Okay? Okay, yeah.
So we use the C1 plus C1 times column plus C2.
If you use the C1, C2, C3, etc., then what you can do is that you find out C1, C2 so that the linear combination becomes 0. But we cannot count how many of them that are linear independent. To count how many of them, then you have to see how many columns that can be expressed as another vector. Okay. So in this case, column 2 can be expressed as multiplication of column 1. Column 3 also as a multiplication of column 1. So only one factor that is independent. Rank is 1. What about B? What's the rank? The rank is 3. So 1 plus 3, you get 4.
Why is it?
Huh?
Why?
Yeah, 3, you cannot express each of these column factor, yeah, with each other. You cannot do that. Yeah, the maximum is 3, you cannot 4. Okay. Now, can you find out the basis for column space of matrix A? Column, yeah, the column, we have 4 columns. Which columns that forms the basis?
For matrix A, column
Which column that forms the basis?
1, 2, and
1, 2, and 4, that's correct. Okay. So, please see here clearly. A has 3 rows, okay? 3 rows, and then 4 columns. The maximum vector space that can be spanned by the column is R3. Okay, the maximum is R3. So the basis must fill up R3 also. Okay, so you choose the 3 vectors linearly independent, then it can span R3, which is 1, 2, and 4. Yeah. Why number 3 cannot be the basis? Yeah, column 3 cannot be the basis. Why?
will not create an identity.
What if it's 1, 3, and
1, 3, and 4.
No, 1, 3, and 4 cannot. 1, 3, and 4 can. Sorry.
yeah, 1, 3, 4.
1, 3, 4 also, it can be a basis. No, what I mean is that why when we choose 1, 2, 4, column 3 cannot be included. Why?
3 and 4 is
No, 2 and 3
Yeah,
linearly
2 and-
dependent. Yeah,
sorry, yeah, 2 and 3.
there is no choice of 1, 3, 4. Yeah, no.
1,
Tapi kalau ada bisa.
But if it is there, then you can choose that.
Also, the number doesn't have to be like 1, 1, 1.
No, yeah. As long as they are linear independent, and then it spans the number of rows or vectors or columns. Yeah. Okay. I want to move first to the inverse because that's easier. Wait. I don't want to add this one first. Easier to get the inverse using Gaussian elimination. So what you need to do is just doing this. Yeah. Let me show you. Wait. This is called the Gauss-Jordan elimination. No, you don't need to compute the determinant in this case. No need. Okay. What is the inverse of this?
1.
So to do that, we first augment the matrix. Okay, we write down 1, 2, 3, 4, and then we write down identity 1, 0, 0, 1. Okay, and then you row reduce this whole matrix until it becomes 1, 0, 0, 1, and this is A1, A2. Then this will be your A inverse. Yes.
Also, the red one will be the A inverse.
Yeah.
By we trying to make the black one connect.
Yeah. You row reduce until it becomes identity.
Row 1. Row 2. We not only do that. We one zeroing the diagonal.
Yeah. Yeah, zeroing this, you have to make this become 0. Okay, what are the rules that you can do? Wait. So we need to do elementary row operation. Yeah. Row swap. Yeah, row swap.
Yeah.
You can do row swap. Wait. Cancellation solving. So we don't have. So you cannot switch the column. Yeah, you can only switch rows. Yeah. An example is this. Let me go to the example. This one. Compute the inverse using Gauss-Jordan elimination method. Okay. Let us do it. Yeah. 1, 3, 2, 0, 1, 0. Okay. No. Row 2 and 3 is already fixed. We only need to change this. So what do? We eliminate this from here. Okay. So row 1 minus 3 times row 2. Okay. Can you see it? Row 1 minus 3 times row 2. What do we get? 1, 0. 2 lah.
1.
And this one 1 0 0 ya. 0 1 0. Okay. What about row 3?
Row 1. Row 3.
Wait. 3 times row 2. Nothing happened ya. Oh no, this happened here. Sorry, it happens there. It's not 0, but it is minus 3 ya. Minus 3 ya. 0 minus 3. Okay, so it becomes minus 3 in here. Okay, and then the last part, 2 minus 2 of 1. Okay, this is R1 minus 2 times R3. So what do we have? 1 0 0, and then okay, so that's the inverse. B12. So this is the A inverse, yeah. A inverse is here. What is B12? B12 is this, yeah.
Row 1, column 2.
Oh yeah.
This minus 3. Okay.
Awalnya row 0. Tadi yang row swap itu kapan kita perlu lakukan?
Iya, row swap. R1 minus 3R.
Row swap is not necessary, yeah. I mean, you can do it. You can do, but not always. What about this?
Alah. Nah, ini kayaknya perlu row swap. If we want to make it one of them, because row swap. Yeah, 2, 1. Perlu swap tengahnya kan?
Okay, I'll give it as an exercise, yeah. What I want to discuss as the last topic for today is how to solve AX equal to B.
AX equal to B.
Yeah, AX equal to B. Now you know a lot already. Yeah, let us discuss AX equal to B. Where is it? Okay. The first condition is that if A is full rank, you know how to get full rank of A, right? How to check whether it is full rank or not? Yeah, if A is full rank, then X is unique. And then when you get an answer, you just write down X is equal to this number, that number, and that number. That's it. Okay, so X is unique, and so the X is called the XP or X particular, yeah. Particular X. However, for the second condition, when A is not full rank, and suppose you have a solution X is not unique. Suppose it has solution X is not unique, you have infinitely many solutions. So you need to solve two things. First, you solve AX equal to 0, and then you solve AX equal to B. Okay? You get what I mean? If A is not full rank, then you need to solve these two. The solution from here is called homogeneous solution, and then in here you have the particular solution. What you need to write down is the total solution. X total is X homogeneous plus X particular. You get it? Why we have to include the X homogeneous?
For I.
Why X particular is not enough for the second case? Brian, any idea? Now, infinitely many solution, right? If A is not full rank, and let's say you have a solution, then solution is infinitely many solution. So you need to write down the homogeneous and also the particular. Yeah. Why this is true? A times xh plus xp equal to b. Why this is true? Why this is true? Let's say xp is the solution to this. If I have xh plus xp as the answer, why this is still correct? Because we have this is b here. What happened with this? Sorry, xp, xh. Yeah, it's gone, yeah, because it is 0, yeah. So it becomes 0 in here. It's because of that, yeah. And then one more term I want to add up is that the homogeneous X lies in the null space of A. Okay, null space. I think I have to repeat again on Tuesday. Yeah.
Yes.
What are the nullity null space? Null space. Okay, I will see you again on Thursday.